In section 5.2.3, we will examine the properties of the graph of an exponential function. Recall that we can have an increasing exponential function or a decreasing exponential function. We will look at both in this example, and thus we will be building a new parent function. Let's begin with f of x equals 2 to the x power. So to graph an unknown function, an easy approach is always to plot points. So we'll pick out some x values and we'll use those to calculate y values. Now I'm just going to use 3 key points, x equals -1, x equals 0, and x equals 1. That will be sufficient to recognize the shape of our exponential function. Now plugging -1 in for x into our function 2 to the x, we have 2 to the -1 power, or 1/2. 2 to the 0th power is equal to 1, and 2 to the 1st power is equal to, not 1, but 2. Let's go ahead and plot these ordered pairs in our coordinate plane. When x is -1, y is 1/2. When x is 0, y is 1. And when x is 1, y is 2. Now, before we connect the dots, I want to point out an important property of an exponential graph. Notice, no matter what value I plug in for x between -infinity to infinity, 2 to the x power will never equal 0. So this function will never cross the x-axis. For that reason, we often draw a horizontal asymptote as the lower boundary line of this graph. The equation of this asymptote is y equals 0. Every exponential function will have a horizontal asymptote as part of its graph. Now, the function gets very, very close to this asymptote over here on the left side, and then begins growing very, very quickly over on the right side. So this is the graph of y equals 2 to the x. The interesting thing about this function is that this is the function that models cell division. Notice if we start out with one cell, that cell grows into 2 cells, those 2 grow into 4 cells. Notice if x is 2, 2 squared would give us 4. So each iteration gives us the number of cells in each process. So again, that grows very, very quickly. And it is modeled by a simple function like 2 to the x. Now, let's consider, what does 1/2 to the x look like? We're going to approach it the same way. Now our base is a fraction between 0 and 1. And we will plot it with the same key points, -1, 0, and 1. So if I start with -1, 1/2 to the -1 power is 2. 1/2 to the 0th power is 1. And 1/2 to the 1st power is 1/2. Now, those numbers should look very familiar. Let's plot them and see what happens. We have ordered pair, -1, 2, 0, 1, and 1, 1/2. Did you notice that our function simply reversed? It still has a horizontal asymptote on the y-axis, but we say this is a decreasing exponential function. So this is our function 1/2 to the x. Now, all exponential functions, increasing or decreasing, will take this basic shape. Let's look at our calculators to explore a few more bases. If we go to y equals, and we type in our function 2 to the x power, and also for y2, let's examine 3 to the x power, what we're going to notice is that the two functions have very similar properties, but one is going to grow faster than the other. If we were to graph 5 to the x or 10 to the x, we would see the same basic properties. We'd see an increasing exponential function, and the horizontal asymptote would still be on the y-axis, and the y-intercept for both cases is the point 0, 1. If I look at other exponential functions with fractions as their bases, 1/2 to the x, 1/5 to the x, the basic shape will be there, but the steepness is what changes. in this case, if we look at both of these functions, the domain of both functions is negative infinity to infinity, and the range is 0 to infinity. Notice the parenthesis with the range. I'm not using a bracket there because the function levels out above the asymptote. It doesn't ever actually reach y equals 0. So those are two examples of basic exponential functions. One is increasing, the other one is decreasing, and all other exponential functions will be very similar to these. So we can summarize the properties of exponential functions. Exponential functions of the form y equals a to the x have three key points. X equals 1, y equals a. X equals 0, y equals 1. X equals negative 1, y equals 1 over a. Now, I don't necessarily recommend memorizing those points. What you do need to know is how to generate an exponential function, and that is by choosing x equals 1, x equals 0, and x equals negative 1. Those were the three key points that we used to find the graphs of our first two examples. The horizontal asymptote will always have the equation y equals 0. And the y-intercept for exponential functions is always 0 to 1. 0, 1. Our domain is negative infinity to infinity, and our range is negative infinity to infinity. Those are the properties of a basic exponential function, but then those properties may change when we introduce transformations in the next video.